All right, folks, continuing with Ampere's law, we're going to go into examples now. So this is Ampere's law part 2, examples. We did the example of a thin sheet, a thin infinite sheet, whereby we showed that the field above and below was, I want to continue with that example a little bit. And what was peculiar about that example is that your current density was into the board this way, okay? Recall the result that we had from the integration. Right? Walk you through it again just to make sure. We created a loop that looked like this, and along that loop the magnetic field was, because of symmetry, pointing this way and that way. One thing we didn't discuss was maybe the field was stronger down here than it was, closer to the current source than it was further away from the current source. This was B, and this is B, and the element of length that we chose was what we had to be along the loop. So dl is this way, dl is this way here. This is why this part did not contribute to the line integral. The line integral here is 0, line integral here is 0, so you're left with b dl up here, b dl up there. So you wrote that, wrote the integral of b dot dl reduced to just the top and the bottom. B and dl pointed the same way here, so that gave you b dl integrated over the length, which was l, and this was, with w, so this was b times l up here, b times l down there, 0 here, 0 there, so that gave you 2bl equal to mu naught I enclosed was j times l. Look at that, part of the video again to make sure that you got it. B was equal to mu naught j over 2. What's really interesting is that there is no dependence on x or whatever this distance is. What this is telling you, basically, this result is that the field here is the same as the field there, same as the field there, same as the field everywhere, because it's an infinite sheet. Remember, the sheet was infinite this way and that way. Now we're going to do the example where we have two sheets. One this way, one that way, with current, two infinite sheets. Current density, again, uniform, J flows into the board. So that is J up here, and the same current density, flows into the board down here as well. We'd like to calculate the field everywhere. It says we find the field everywhere. These sheets are infinite this way and infinite that way. What are we going to do to calculate the field around these current sheets? Well, we take an Amperian loop, and by now we understand that it must be a rectangular Amperian loop, right? So I'm going to show you two ways of doing this, right? One is, let's take an Amperian loop that looks like this. Okay, nothing wrong with that. What do we know about the field? Because these things are infinite, right? We can garner from that the field, above and below the sheet is going to be the same. So uniform. So B this way. You could use superposition to do that as well. But let's say that you don't want to use superposition. From superposition, it's pretty easy. Using superposition, we can tell that what the field is going to point this way from the guy on the bottom, and this way on the top should be 0 in here, and should be twice the field up and below, up and below. Just like having two infinite planes of charge, the field out here will be twice that of why? Because one interesting fact that we found from for infinite sheets was that the field from an infinite sheet, you have a sheet of current, a sheet of charge. The field here is the same as the field there, same as the field there, right? So you put another sheet, and the field is same from the sheet, same here as that. So you just double the field. So what are we going to do here? Let's say that we don't know this. We don't know how to use superposition. Nobody taught us that. And we want to just use Ampere's law to find the field above and below these sheets. I'm going to draw my Amperian loop in two ways. One way is going to take this Amperian loop here, right? And that Amperian loop has length L, and again with W. Okay, I want you to think about, take a minute on your own, please, to write down what write down Ampere's law, apply it. Like I'm going to stop, maybe shouldn't stop because of the video, but stop the video now for 2 minutes and do this on your own. Okay, instead of us wasting video time, like we do in a lecture, you can do this on your own, but please stop the video and do this calculation on your own, starting with Ampere's law. So I'm hoping you stopped the video. If you didn't, that's fine. So we picked an Amperean loop with L, length W, or whatever. We say what? The integral of B dot dl along this loop is going to be equal to mu naught I enclosed. Okay? So B dot dl is what? You got, well, B here, and B dot dl is, you know, from symmetry, we're not sure if B is 0 or not. Let's say we don't know superposition. But we know that B is going to point, because of symmetry, perpendicular to this loop. So the integral of B dot dl here is 0. Right? And over here, B points that way too. So B dot dl is also 0, here and there, and there and there. So we're left with, again, just like the same as that problem, we're left with B dl up here, B dl down there, integrated. The angle is 0 between B and dl up here, and the angle is 0 between B and dl down here. You integrate that, you get B times L up here, B times L down there, and that's going to give you, well, the integral, B dot dl, becomes, therefore, what? B dot dl is B times L up here, B times L down there, nothing here, nothing there. And because of symmetry, we know it's the same B. Again, B points that way, and dl points that way. The angle is 0, so it's just B dl, B magnitude, dl magnitude, cos 0 is just B dl. Integrated over the length is just, you know, B is uniform, comes out of the integral. B integral dl is just B times L, B times L. So 2bl is equal to, now the I enclosed is what? 2bl is equal to mu naught I enclosed is, I have the I enclosed in this loop is what? I have J times L current density. Current density, remember, because these are thin sheets, the current density is given in J in amps per meter, right? So the amount of current that sits in here is not J times A. There is no A to speak of. It's just J times L and J times L, so that's equal to 2JL. And that gives me a field that is equal to mu naught J. 2 is cancelled, L is cancelled, L. Right? So, as expected, from one sheet I get B equal to mu naught J over 2. From 2 sheets, because these are infinite sheets and the field above this sheet is the same everywhere, the field above the sheet is the same everywhere, you just get 2 fields. Right? But it's a nice exercise in using an Amperian loop here. Okay? Next, so stop the video, make sure you understand this part. Next we're going to do it a slightly more interesting way, and that we're going to take a loop that takes us inside the region between the two sheets. In here, I'm going to look for blue. My blue, where's the blue? I'll be right back. Okay. So I got me some more colors. Over here, remember these are infinite sheets. So what I'm going to do here is take a loop that looks like this. My loop looks like that. It takes me smack in the middle between the 2 sheets. Why is that important? Let's recap on how we choose the loop. We choose the loop in such a way that the field magnitude is uniform around the loop, right? So it's uniform, it's the same here as it is there, and it's the same everywhere. So that's good. How do you choose your loop? How do you choose your Gaussian surface? Again, you want the Gaussian surface over which the field is uniform, and the angle is 0 between E and dA, or 90. Same here. You need a field, you need a loop over which the field is uniform, that's uniform, and here, you know, uniform, and the angle is 0 between the field and the element of length, that is true here and there, or the angle is 90 between field and element of length. What is element of length here looks like this. This is dl, and the field is either 0 here or perpendicular. Here it's very clear. dl is this way, and B is that way. So the field B is going to be same magnitude as the, you know, up here. But the angle is 90. Integral B dl is 0 here and there. So how do we pick our Amperian loop? So that the field is parallel to the loop. The field magnitude is the same all over the, you know, segments of the loop, right? And the angle between the field and the loop is 0 or 90. Right? Why did we have the loop run through the middle here? Because the magnitude of the field here is uniform. As a matter of fact, when this guy is smack in the middle between the two, like I'm taking the loop here to be more accurate, the loop is going to run me right through the middle. This is, if this distance is d, okay, this distance here is d over 2. Okay? Why am I? Because let's say I'm a bit confused about superposition. I don't know that the field from this guy and that guy can cancel in this whole region. I'm not sure about that. Right? I'll take my loop to look like this, so that if I'm not sure that the field is going to be 0 in between everywhere, which it is, right? Because again, the field from this guy is going to be pointing this way. Sorry, it's going to point that way. Right? From the bottom sheet is going to point that way. From the top sheet is going to point that way. And these are infinite sheets. The field magnitudes are uniform. No matter where you go, the field from this sheet is the same here as it is there, as it is there. The field from this sheet is the same here as it is there, as it is there, pointing in opposite directions, so you should get 0 in between. But let's see, we don't know that. We know for a fact, though, that we put the middle point, or the middle segment between the two sheets, that the field should be 0 here. So what have we done? We picked an Amperian loop over which the field is uniform up here. The field is uniform 0 down here. And the angle between the field and the loop is 0 up here, and maybe 0 down here, 0 anywhere. And the angle between the field and the loop is 90 here. So these sides will not contribute to the integral of b dot dl. Field is 0 here. All I have left is what? Just b times l. So how does that work? Well, we say now that the integral of this blue loop with blue ink, the integral of b dot dl over my loop is equal to mu naught I enclosed in the loop. Okay, my loop is here now. We're playing games with loops, right? So if the loop length is again L, okay, then I have b dl, b this way, dl this way, b dl cos 0. So b dl integral, b is uniform, comes out of the integral, b times l. So this reduces to b times l. B times L equal to, now the current enclosed is equal to what? Mu naught times the current enclosed is J times L, and that gives me that B is equal to mu naught J as well. That's really nifty. Okay? Alright, so we're going to do another example in a minute after this pause.